have this nice theorem that you should remember, okay? So if you have U and W as subspaces, and if their intersection is just 0, then we know that U plus W is equal to U direct sum W. Okay, so this is an often handy way of proving something is a direct sum if you just have 2 subspaces. Unfortunately, if you have 3 subspaces, such a thing is not so simple to write down. So there you have to use the definition of the direct sum directly. But here, this is a nice thing to use. Okay. So let's try to think about what this space is. Before even trying to show something, you should try to think about what this V is, and then after that get some hints of what other approaches you can do to get W. So can you represent V as a span of 2 vectors? So you can rewrite this as x, 0, x, x, plus what?
0, y, negative y.
So that's going to give you 1, 0, 1, 1, x times, and then y times 0, 1, 1, negative 1, right? So these are the 2 vectors that's going to span V, and it's obviously linearly dependent, so these are like the bases, although we're not allowed to say bases yet. So can we think of some vectors that's not in this span? Give me some vectors that's not in that span. Give me anything. Come up with something simple.
0, 1, 0, 0.
Yeah, 0, 1, 0, 0 definitely is not in the span. There's no way to make that work. Can you give me another one? Well, think of it this way. If you have dimension 3 and you have a hyperplane, you have a plane, if you pick random points in R3, is there a bigger chance that this random point lies inside the plane or outside the plane?
Inside the plane.
No, this, like, to be on that plane, it has to be it has to satisfy some relationship, right? Most other, you have a lot more points outside the plane than inside the plane,
Oh, yeah.
right? So in other words, this is like dimension 2 and dimension 4, so most likely you pick some random thing, it's not going to be in here. Okay. In other words, if you put 1, 0, 0, 0 and 0, 1, 0, 0, you'll find that both of them are not in here. Neither is 0, 0, 1, 0 and 0, 0, 0, 1. All of them, you try and you'll find that it's not in there. So let me try to convince you that. For example, I claim that 0, 0, 0, 1 is not in that span. Let's say it is true. Well, if this is in that span, it has to equal to this. Now, the first coordinates being equal forces x to be
0,
0, and then y has to be
0.
as well. Then if you set x and y to be 0, can it equal to 1?
No.
No way, there's no way to do that, right? Same thing here. If you had 1, 0, what's going to happen? There's no way to get that working, right? Yeah. And you can also do 1, 0, 0 same way. All of these, you're going to see that, okay? So you can basically pick W as any of those two vectors and it's going to work. So there are like infinitely many choices for the W. You can choose W to be, say, for example, span of 1, 0, 0, 0, 0, 1, 0, 0. That's like one possible answer. Okay. Or another possibility is like span of 0, 0, 1, 0 and 0, 0, 0, 1. That's another possibility. Of course, these two are different, okay? Yeah. I'm not saying that those are the same, but they're different, but yet they satisfy the condition of the question, okay? So let's do this. I'm going to work with the second one. I just have a feel that this might be simpler to do. But you could also do the same thing for this one. You can choose any one of those, okay? So I'm going to show you the solution with this being my answer. But once I'm done with this, try to see if you can do the same thing with the first guy, okay? Either one should work. And by the way, there are two ways to write down this W. The W, you can write it as a span of 0, 0, 1, 0, and then 0, 0, 0, 1. That's one way, but you could also rewrite this as W equals to A times this one and B times that. If you do that, what do you get? 0, 0, A, B, right? Yeah. So that's another way to write it. If you multiply it by A and then B and then you add them up, you get this. So that I think that's an easier one to do. Okay. So solution. Let W equals to 0, 0, AB with AB in R. Okay. If we didn't have a discussion and I just wrote this down, you'll have no idea what's going on. Okay? That's why just reading a solution is not enough. Anytime you have a question that you want to try out, reading a solution is not enough. You really have to think about why that somebody started with this. Okay? Solutions only give you like half of what should be really said. Okay. So obviously this really means W is a span of 0, 0, 1, 0 and 0, 0, 0, 1. And I want to show that anything in R4 is a sum of a vector in here and sum of a vector in here, right? Okay? And one important thing is I didn't want to use X and Y. If I use X and Y, there's X, Y, and Y here, so it's going to confuse us. So that's not what we want. Then I'm kind of out of letters now. So for any vector U in R4, U is equal to, let's write down U1, U2, U3, U4. So it kind of sucks because I want to do A, B, C, D, but I already use A and B. So maybe a cleaner solution would have been X and Y for these guys and maybe use Z and W for this other guy. That might have been better. Okay. But I ran out of letters, so I'm just using U1 through U4. And by the way, this is not in print, but if I was writing this in print, we're using boldface for vectors, right? lowercase boldface for vectors, and this will be regular font. So, well, not in our textbook, but a lot of other textbooks do that. Okay. All right. For any u in R4, u should be like 4 numbers, where ui's are in R. 4 real numbers. That's what it is. Okay. Now, let's see how we can represent u1, u2, u3, u4 as something times x, y, no, not something times, sorry. X, y, x plus y, x minus y, plus 0, comma 0, comma a, b. And you shouldn't be writing this right next to that one, okay? You should be writing this in the corner of a page so you can erase it later, okay? Okay, so if I compute this, what do you get? You get x, y, and then you get x plus y plus a, comma b, a, comma x minus y plus b, right? So x has to be
0.
u1,
Oh, sorry.
y has to be u2. A has to be, now that's a trick question. A has to be
U3 minus x minus y.
but x is u1 and y is u2, so u3 minus
U1
u1
U
minus u2. Okay. And then b has to be
plus x.
u3
So
minus
then
u1, and then what are we doing here? We want this to be this, right? Oh, that's not u3, so
Yeah, it's
that's
U4.
why you're u4. Okay, good. So u4 minus
U4 minus U1 and plus U2.
plus u2. Okay. You see that? Okay. So this is not the calculation you want to write down. Instead, you want to say this. Then u1, u2, u3, u4 is equal to u1, u2, u1 plus u2, u1 minus u2, plus 0, comma 0, comma u3 minus u1 minus u2, comma u4. I'm running out of space, so let me write small. Let me write this again. u1, u2, u1 plus u2, u1 minus u2, plus 0, 0, u3 minus u1 minus u2, u4 minus u1 plus u2. How did we get that? Well, we did it by doing a computation somewhere else, okay? And now what do? You erase your tracks. There's a famous saying about the mathematician Gauss by another person. When asked about Gauss, this another person said, I forgot who it was. Another person said, he's like a fox. He knows how to erase his tracks. So he would like do this kind of proof where it seems like the rabbit is pulled out of the hat. You don't know where this came from. Okay? There was some work behind the scenes. But now, why are we doing this? What does this do? First, is this true? If you add these two, what do you get? u1 plus 0 is u1, u2 plus 0 is u2, u1 plus u2 plus u3 minus u1 minus u2 indeed is u3. u1 minus u2 plus u4 minus u1 plus u2 is indeed u4, right? So this identity does hold. But so what? What does that prove us? What does that tell us?
This, also, the U use
Anything that looks like this belongs where?
also W.
No,
The V.
belongs to V. Because V is what? X, y, x plus y, x minus y, right? So with x being u1 and y being u2, perfectly makes sense. Right? Okay, and then anything that looks like this belongs where?
W.
In W. Right? Because anything that has 0, 0 with whatever and whatever, that belongs to W. Right? Okay? So what did we just prove? We just proved that R4 is indeed a subset of V plus W. But, V and W are subsets, so we know that V and W, this is true, right? So, let's see, this is what we know, but since V plus W is in R4, if you add any subspaces, it's always in the enclosing space. So that says that V plus W is indeed R4. Okay, so we're getting close. What do we still have to prove?
Then V intersection of W is the
0.
zero.
To show that it's a direct sum, I said for two subspaces, it's good to just say that the intersection is 0, right? So furthermore, if U is in V intersection W, okay, that means U has to be representable as x, y, x plus y, x minus y, but it should also be representable as 0, 0, A, B, right? So for U to belong to V, this is the condition. It has to look like this. To U to belong to W, this is the condition, right? So therefore, these two have to be equal, but that means x is 0, y is 0, x plus y is 0, x minus y is 0, and then A is 0, and B is 0, right? Right? See, 0 has to be x, 0 has to be y. If that's true, then x plus y is of course 0, x minus y is 0, but if these are both 0, then A has to be 0, B has to be 0. Okay, so we have shown that U is equal to 0. Which means V intersection W has only one element. Because anything you choose from here is always 0. V intersection W is 0. That means V plus W is really a direct sum. Okay? And therefore, have you seen this triple triangular dots? That means therefore. Okay, so therefore, U plus V plus W is R4. Okay. So that's it. The answer is, let's